Hello, welcome to this session where SemiDynamics is introducing its high bandwidth vector capable RISC-V cores. I'm Roger Espasa and I'll walk you through this presentation. First, a quick word on SemiDynamics. It's a European-based IP provider founded in 2016 in Barcelona. And actually one of the cores we're going to discuss today, Avaspado, is being used by the European Processor Initiative in its accelerator. Let's get to the new cores being introduced today. First, we'll talk today about Avaspado 220. It's a 2 wide in order core. It comes with the technology we will describe called gazillion misses, which allows it to make very good use of your memory system. And it also comes with RISC-V vector support with the upcoming 1.0 spec. We'll also talk about Atravita 220, which is our 2 wide out of order core. It also has gazillion misses, and it also has RISC-V vector support. So what is a high bandwidth core? Why do we call our cores high bandwidth cores? In short, a core that's as high bandwidth it has lots of outstanding memory requests. And we like to call that a core with a gazillion misses. How is that useful? We have here an example to gather sparse data, right? On the left, we have a program that does a couple loads. In fact, one of the loads is indirect, so it's sparse. Then you compute on that data and you store. And to the right, you see a stylized assembly code. It's close to RISC-V. And you can see the key thing where there's a load first of the index data, then you load an indirect load based on that X5 register, then you load B, then you compute and store back. So there's 3 loads per iteration. How's that going to work on a normal microarchitecture? Well, let's pick an example. Let's make a decision. Let's say that 2 of those loads are going to miss, roughly speaking. So over time, what your most microarchitecture is going to do, they're going to do the 3 loads, 2 of them are going to miss. And so there's going to be 2 requests going out to the memory system after those cache misses. Let's say your microarchitecture is capable of unrolling this loop up to about 4 times, more or less, right? Doesn't matter the details. So there's going to be, you're going to be able to unroll these 4 times and do all the way up to 8 requests to the memory, which is great, right? Now, after the 8th request, most architecture will just stop. And they'll wait for what? Well, they'll wait for the first piece of data to come back from the memory system, which is far away, right? So there's going to be a long wait time, L cycles, where L is your memory latency, and typically that's over 100. Then data will come back, and at that point, some resource on your microarchitecture, typically an MSHR, is going to be free, and that will allow you to make your 9th request and resume your program execution. Right? Obviously, the long gap in the center of this picture is undesirable. The bigger that gap, the worse. You have more latency, so your program is slower. And while that gap is happening, you're not making requests to your memory system. So your memory system bandwidth is going unused. So that's very undesirable. What is the technology we have, the gazillion misses technology? Using the same example, how does it change things? Well, in the same conditions, let's say 2 of those misses are going to suffer a cache miss. We would, launch 8 of those misses. But unlike conventional architectures, we have the capability to keep going, to keep making requests all the way until we've launched 128 requests to the memory system. So we don't stop, we just keep going. Now, data will come back roughly at the same time. This doesn't change when data comes back, but the huge difference is that the wait time, the time where nothing's happening, the time where your memory bandwidth, your memory system is unused and nobody's doing anything, is greatly reduced. We've used all that great gap of many, many cycles to actually send requests to the memory system. Thereby, we've reduced the perceived latency of that memory system, and we've increased the bandwidth you're extracting from your memory system. Like other microarchitectures, as the first data come back, we can launch our 129th request to the memory system, and so on and so forth, right? If you have vector instructions, if you have a vector unit, which we'll talk about in a second, this technology shines even more because, if you consider RISC-V VLX EI32 instruction, which is a gatherer, and you assume a VLAN of 512 bits, and that instruction will make 16 requests to the memory system. I'm assuming it's a gatherer, so each request will go to a different cache line, right? So again, same thing, as opposed to stopping on the 8th request. So as opposed to your microarchitecture actually stopping in the middle of the instruction and waiting for data to come back, we'll be able to submit all 16 requests to the memory system. In fact, if you have more gatherers, or if you've unrolled the loop, we'll be able to support multiple of those gatherers all the way until you use the 128 requests we've provided. Okay. By the way, small detail, at larger VLANs, if you have bigger vectors or smaller indices, the benefits are obviously even more, right? So let's compare that to other cores, right? In this chart, we're going to plot different cores on the market. Their retirement issue with is on the x-axis, and the number of outstanding misses they support is on the y-axis. Let's start with the Power 9. It's a 6-wide out-of-order core and can support out to 16 outstanding miss requests, right, to the memory system. The Intel Ice Lake is a 5-wide out-of-order core and can support 12 requests to the memory system after a cache miss. The RMA76 is a 4-wide out-of-order core and can support 20 outstanding requests to the memory system, so bigger than the previous two. And if we move now to RISC-V, those three are obviously non-RISC-V cores. If we go to RISC-V, we plot on the chart the RISC-V Boom from Berkeley. That's a 4-wide out-of-order core with 10 outstanding cache misses. And then we've plot also offerings from Sci-5, from Syntacore, and from Andis. We do not know exactly their number of outstanding misses. That's not public, but we know their width. So we've plotted them more or less where we expect them to be. In comparison to these cores, where are the two cores we're introducing today? Well, the Avaspado core supports 64 outstanding misses to the memory system, and the Atravito core doubles that all the way to 128. So you can see that in any environment where high bandwidth is required, where sparsity is a characteristic of your application, those two cores will really stand out compared to the rest. What is it good for in terms of in the applications domain? Well, we think this technology is going to be great for machine learning. We all know those big tensors are not going to fit within a small cache, or even if you have on-die scratch pads, it's very, very likely that those tensors will overflow those scratch pads. So having a gazillion technology allows you to actually use those tensors that are in memory and bring them into your core without stalls, right? Within the machine learning domain, a very important subdomain is recommendation systems, and those are almost by definition very, very sparse. So that's a domain where our technology is going to shine even more. It's going to be more useful, right? At a different scale, key value stores, and I fully understand that a key value store system is far more than just the core. It's a full system, many storage, networking, many things. But at the core, at the fundamental core, it is a sparse environment, because you're making requests on these random keys, or not random, but randomly distributed in your key value store, and you don't want to wait. You want to make lots of key requests, get the values back, and then operate on them. So again, we think our technology will work great there. And goes without saying, the name says it all, but in the HPC domain, there's tons of sparse data. And again, the ability for both vectors and scalar to do those sparse requests is going to be great. If you're an SoC designer, rather than thinking from the software point of view, how can this help you? Well, think of it from the point of view that you're building an SoC with limited SRAM or cache. What would you do? Normally, you would just slap in there a DMA. And you would say, no problem, I'll put a DMA and I'll bring data from the DR into my core and then operate from there. That's fine, but those DMAs are hell to program, and your software team, they hate those DMAs, right? So instead of using a DMA, if you use our core with a gazillion misses, you will have a very easy software environment for your software team, easy to program, easy to request lots of data, and you know the core is not going to stop. So you'll be able to use that DDR bandwidth. On the other extreme, let's say you're building an extreme high bandwidth system with 6 HBM2 dies connected to your SoC. Well, in that scenario, also our technology is great because you have tons of bandwidth. Those HBMs can deliver tons of lines per cycle, and you want the core capable of actually making those requests and not just stalling on the first problem it encounters after a few misses. So again, in the other extreme of this spectrum, our technology is great. And if you decide to use one of our vector units, then the technology shines even more because vectors naturally make lots of requests. So you put a vector unit that's capable of doing lots of computes, and then you couple it with our gazillion technology that guarantees that those vector loads, vector gathers, will go all the way out to your DDR system without stalling and keep the vector unit fed as all the time, right? So we think that in your next SoC, our cores are going to be very interesting. Let's get into the Avaspado core details. As I said, the Avaspado 220 is our in-order core. It's a RISC-V 64 GCV, so fully capable of booting Linux. The front end is organized in roughly 4 stages: PC, then we read iCache, ITLB, and branch predictor, get 64 bytes out of the iCache. We put those into a queue, we get 8 bytes out of the queue, and the decoder transforms those bytes into 2 instructions every clock. It's worth noting it supports SV48, 16 kilobyte iCache, and as I think I said, it decodes the upcoming 1.0 vector spec. From the decoder, we go into 3 queues. These are shallow queues because this is an in-order core: the MIQ, the GIQ, and the VFIQ. The GIQ feeds the integer subsystem, so all integer instructions go here. The MIQ feeds the load store unit. The load store unit is a deeper pipeline, has an AGU, which in fact is capable of supporting vector load stores, gathers, and scatters, DTLB, Dcache, and then alignment network. If you miss in the Dcache, you go into the gazillion subsystem, and from the gazillion subsystem, you go into the coherent interface of your choice. Worth noting, Dcache is 32 kilobytes. We have full hardware support for end-of-line accesses, no trapping, and talk to us to what coherent interface you would like. We can adapt our interface to whatever you need. Finally, the VFIQ, if you will, drives the floating point unit in there. Now, if you have, we'll talk about in a second about the vector unit, and then I'll show again where the vector unit is connected here. As any IP, the following things are customizable upon request. Let me introduce the RISC-V vector processing unit, our VPU. Well, the SemiDynamics VPU, it implements the RISC-V, the upcoming RISC-V Vector 1 spec, including LMOL, segmented loads. We do not have Vector Atomics support currently. We'll be happy to talk to you if you need it. And it's ready for out-of-order support, so it's ready for renaming. It's customizable, so you, the customer, decide how big those vector registers are going to be, from 128 bits to 4096, and how wide the data path is going to be. I'll show that in the next slide in a second. Also, worth noting is that we have a fast cross-lane network for the compress, expand, gather, and slide instruction, gather and slide instructions. That's actually pretty useful, and we hope to have it available, as soon as 3 months after the VSpec freezes. So as soon as it freezes, we'll be ready to deliver to our customers. A quick block diagram on that VPU. It's lane-based, so it's organized in lanes. So you, the customer, decide how many lanes you want. That sets your total data path width. We can support all the way to a full cache line coming from the Dcache into the lanes, although there's only one arrow there. It talks to all lanes, and each lane has a portion of the register file, of the vector register file, and has the units you would expect, right? The FMA for floating point compute, integer divider, and the XL unit, which is the one that provides cross-lane connectivity between all lanes. And the XL network is the one that connects each lane. So now let me show you how that connects into Avaspado, right? That's the same picture I showed you a second ago. And basically the VFIQ, the vector floating issue queue, actually holds instruction for both floating point unit and the vector processing unit. And the vector processing unit is directly connected to the coherent interface, so you it gets data from the cache or from memory as it comes in. As I explained before, VLoads go on through the MIQ, through the vector unit, and deliver the data to the vector processing unit. Let's move on to the Atrevido core. The Atrevido core is our out-of-order core. So it has a very similar pipeline to actually Avaspado. However, it's deeper pipeline, so that we've added stages both to the front end. We've added, obviously, a rename stage to rename registers. It renames scalar, floating point, and vector registers. We've added obviously a register file that's bigger than the ISO requires to support renaming. And we've also further pipelined the load store unit to make sure that Atrevido will be at a higher frequency point than Avaspado. It shares the other characteristics. It has you can choose the coherent interface, full hardware support for analine, 32 kilobyte Dcache, 16 kilobyte iCache, and SB48. And relative to Avaspado, it has larger branch predictor, and obviously renaming and retirement logic. And like Avaspado, once the vector spec is frozen, we will soon after offer Atrevido with a vector unit, where the vector unit will be fully renamed and will be connected just like we've already discussed. And with that, let me go into the summary. We've talked about the two cores being introduced today, plus our vector unit. The Avaspado 220 is our 2-wide in-order core, supports gazillion misses, which, as we've explained, we think they're great for high bandwidth memory systems, for memory systems that have a long latency, for any SoC that wants to achieve a great efficiency from their memory system. Gazillion misses is going to be great. And both Avaspado and Atrevido support the vector processing unit we're introducing today that will be available as soon after the spec freezes. And we've also discussed Atrevido, the Atrevido 220, which is a 2-wide out-of-order core, also supporting gazillion misses and supporting also the vector processing unit we've discussed today. Thank you for listening, and we'll be very glad to answer further questions at any of the addresses below. Thank you very much.